Here I'm going to look at a Leaving Cert past paper question on equilibrium. It's from 2018, question 9. It starts off in the usual manner. What is meant by a chemical equilibrium? I've discussed this in a few of the videos. An equilibrium is set up when you have a reversible reaction. So that's a reaction where the reactants can turn into products, but also the products can actually turn back into the reactants. So when you have this reversible reaction, the rate of the forward reaction is equal to the rate of the backward reaction. That's what happens when a system is in equilibrium. What that means is that you've got a constant amount or constant concentration of reactants or products at equilibrium. Okay, so the easiest way to answer this is just to say that the rate of forward equals rate of reverse or backward. Okay, rate of the forward reaction equals rate of the reverse reaction. Next part is to write the equilibrium constant Kc, which is again that comes up all the time. Kc is the equilibrium constant, so that is going to be equal to the concentration of the products, which is phosgene, COCl2, square brackets indicates concentration, power of their stoichiometric equivalent, and that means the number that's in front, but because there's no number in front of each of these, it's just a 1, so to the power of 1, all divided by the concentration of the reactants multiplied by each other. It's going to be that divided by concentration of carbon monoxide times the concentration of chlorine. Okay, so Kc, our equilibrium expression, is equal to that. Under certain conditions, in a closed container, the equilibrium is green. I can explain the effect. On the colour of the equilibrium mixture, if the pressure is increased by reducing the container size. So that's one way of increasing the pressure, reducing the volume. Here, what happens is that as pressure is caused by the molecules, the gaseous molecules, the sides of the container, increase in the number of molecules hitting off the sides of the container will result in an increase in pressure. So if I increase the pressure, according to Chatelier, the system would look to decrease the pressure. And the system can only decrease the pressure by creating fewer molecules. And that means it has to favour the reaction that produces the fewest number of molecules. So here, as you've got 2 moles on the left, so a mole of carbon monoxide and a mole of chlorine, but 1 mole on the right, there are fewer molecules on the right hand side, so the system will counteract that increase in pressure, favouring the reaction that produces the fewest number of moles. So it's going to favour the production of Cl2. So therefore the reaction is going to become more colourless. Part 2. Explain the effect on the equilibrium yield of phosgene using a higher temperature. So if I use a higher temperature, the system will want to reduce the temperature, so therefore it will favour the endothermic reaction. If you look, the forward reaction here is exothermic. So the only way to cool down is to favour the backward reaction, endothermic, because in endothermic reaction the temperature decreases. The system will cool down by favouring the endothermic reaction, which is the backward reaction, and therefore the overall yield of phosgene will actually reduce. So we get a lower yield of COCl2 as system favours endothermic because it will want to cool down. Part 3. The effect, if any, on the value of the equilibrium constant Kc of using a charcoal catalyst. Well, a catalyst does not impact the value of Kc. In fact, it doesn't even impact the position of equilibrium, but it will allow both reactions to establish equilibrium quicker. So there is no change in Kc, but an equilibrium will be established quicker. So no change in Kc, equilibrium is established faster. So it speeds up both reactions equally. D. This is our Kc question. So a 12 litre container was filled with 0.2 moles of chlorine and 0.2 moles of carbon monoxide. Calculate the value of the equilibrium constant for the reaction if 85% of the chlorine gas had reacted when equilibrium was reached. Okay, so this is a question where we're not actually asked to find the number of moles and we're not given Kc, so we're just asked to work out what Kc is. So I'm just going to go through this down here. So we will keep an eye on our equilibrium expression when answering this question. So I'm just going to go through in detail how to answer this. So we're going to draw up a table, and we're going to start with the mole at start, and we're going to be looking at our reactants, which is carbon monoxide, chlorine, and phosgene. So the number of moles at the start, 0.2 moles of chlorine, and there's 0.2 moles of carbon monoxide. Well, there's 0 moles of phosgene at the start, okay, before they've reacted. The value of the equilibrium constant for the reaction at this temperature. So 85% of the chlorine has reacted. The next step is to work out the equilibrium number of moles. So at the start, we're told that 85% of carbon monoxide has reacted. So therefore, if we start with 0.2 moles of carbon monoxide, we are going to use up 85% of that. That means that we must have 15% of it left. So if we have 15% of 0.2 left, 0.03 moles of carbon monoxide at equilibrium. Now, because it's a 1-to-1 reaction, if I have 0.03 moles of carbon monoxide there, I have 0.03 moles of chlorine there, because it's the same number of moles. Now, how many moles will I have of phosgene? Well, if I used 1 mole of carbon monoxide, I would form 1 mole of phosgene. I don't use 1 mole of carbon monoxide. I use 0.2 minus 0.03, which is 0.17. So therefore, the moles of phosgene must be 0.17. So I now have the number of moles of each of them. But as the expression for equilibrium states, we need to have the concentration of those. And we're told it's in a 12-litre container. So we're looking at the concentration at equilibrium. And this is important because we don't have the same number of moles on either side of the reaction, even though it's a 1-to-1-to-1. So we have to include concentration, and the concentration is the number of moles divided by the volume, which is 0.03 divided by 12, because it's 12 litres or 12 decimeter cubed. Remember, concentration is just moles divided by volume in decimeter cubed or litres. So the concentration of this is 0.03 divided by 12, and the concentration of this is 0.17 divided by 12. So Kc is equal to 0.17 over 12 divided by 0.03 over 12 times 0.03 over 12. And just putting that into the calculator, I have a figure of 2666.6 recurring. You're not asked to leave it to any decimal places. So that is the units. That is our Kc. Now, if you're looking at units for Kc, we've got concentration divided by concentration times concentration. So the units are actually going to be mole minus 1 dm cubed. And the last one now, Le Chatelier's principle predicts best yields in certain equilibrium process at low temperatures and high pressures. Suggests reasons why these conditions might not be used industrially. So this question usually refers to a rate of reaction. Well, if I want to use a low temperature, the reaction could be too slow based on the rate of reaction. So I don't want to do that. So we might need to compromise and increase the rate. High pressures, well, while that might speed up the rate because it brings the reactants closer together and we might get more collisions, high pressures generally tend to be either costly for the equipment or else dangerous. Okay, so for safety reasons, you mightn't use the high pressure. And that is that question.